Hello everyone, I'm Devarati and today I'll be talking about approximating LCS and alignment distance over multiple sequences. This is a joint work with Barna Saha. So in this problem, we are given m strings, each of length n over some alphabet set sigma, and LCS and alignment distance, they are two different measures to find the similarity and dissimilarity among these strings. So formally, the LCS is the longest subsequence that is common to each of the input strings. So for example, here the longest subsequence that is present in all of them is ETION, and that's why the LCS length is 5. Whereas alignment distance is a complement problem where we try to measure the minimum number of characters that are required to be deleted from each of the input strings so that we can make them look similar. So here, as because we have to delete 4 characters, that is why the alignment distance is 4. Both these measures, they have huge application in bioinformatics. And one such example is where we are given a set of genetic sequences of different members from same family. And then we can find the commonality of the sequences and predict their behavioral and physical similarities by finding this commonality among the strings. And this is specifically very important for early detection of different genetical diseases. So there is a classic dynamic program algorithm that computes exact value of alignment distance and thus LCS in time n to the power m. So if this m is large, so let's say if this m is polynomial in n, then this running time become exponential. Moreover, as because this problem has shown to be NP hard, there cannot exist any efficient algorithm. On the other hand, from the fine-grained complexity point of view, the celebrated result of Abbott, Backus, and Williams says that unless the strong exponential time hypothesis is false, there cannot be any algorithm computing the exact value of alignment distance and LCS in time n to the power m minus c for any constant c greater than 0. So we cannot even hope for an algorithm with running time n to the power m minus 2. So the next natural direction that one can think of is designing efficient approximation algorithms. And in this regard, there is a pretty straightforward algorithm that uses triangular inequality, and it provides C approximation of alignment distance in time n to the power m over c. So in next few slides, I will provide a brief overview of this algorithm. So in this algorithm, we start by partitioning these m input strings into C groups, where each group is having m over c strings. Then in round 1, we try to find an optimal alignment of all the strings that are present in group 1 and let A1 be such an alignment. And then in round 2, we find an optimal alignment among all the strings that are present in group 2 and alignment A1 given by G1. And let this alignment be A2. And then we pass this A2 to group 3 and we continue this way until in the last round, we find an optimal alignment among all the strings that are present in group C and the alignment AC minus 1. And let this alignment be AC. And then we output this AC as our approximate alignment for all the strings. And what we can show is, as because there are C groups, we can apply triangular inequality C minus 1 times. And in that way, AC provides C approximation of total alignment distance. And moreover, as because each group is having m over c string, so in every round, we need to compute the optimal alignment distance of at most m over c plus 1 strings. And that can be done using a dynamic program in roughly n to the power m over c time. And as there are C groups, so considering C to be constant, we get our required time bound. So now if I take this C to be 2, then what we can say is that this easy algorithm, this provides 2 approximation of alignment distance in time n to the power m over 2. Now going below this 2 approximation or breaking this triangular inequality barrier is one of the challenging open question. And in our work, we provide an algorithm that provides strictly below 2 approximation of alignment distance in time roughly n to the power m over 2, provided one of the input string is pseudorandom. Now we call a string to be pseudorandom if the following property is satisfied. So if I consider any pair of disjoint substrings from the pseudorandom string, then they must be at large alignment distance. So this pseudorandom model is also famously known as smooth complexity model. So the smooth complexity model is quite well studied when we consider two input strings. And the first result of this type was given by Anthony and Krautgammer, where they considered two input strings, where one input string is pseudorandom and another input string can be any adversarial string. And for this input, they provided constant approximation of edit distance, which is a close variant of alignment distance in almost linear time. Very recently, there is a new work where authors consider a similar model where they consider one adversarial string, and for the other input string, they took a random permutation of that string. And given these two strings, they provide 1 plus epsilon approximation of both edit distance and longest common subsequence in subquadratic time. Now, the question is, what are the interesting properties of the pseudorandom string that are exploited by all these algorithms? Now, remember, by definition, if we consider any pair of disjoint substrings, let's say S1 and S2 from the pseudorandom string, they must be at large distance. Now, if we consider a substring X from the adversarial string, then we can say that there can be at most one substring in the pseudorandom string, which can be close to X or whose distance is very small to X. Otherwise, if there are two strings, let's say S1 and S2, and both of them are close to X, then by triangular inequality, S1 and S2, they are close as well, and we violate the definition of pseudorandom string. So now once we can define that for every substring in the adversarial string, there is a unique match in the pseudorandom string. And if we can find such an unique match, then in the rest of the string, we can restrict where the rest of the string can be matched in the optimal alignment. And accordingly, we can recurse in the rest of the string, and we can show that following this process, we can provide constant approximation of edit distance in quite faster in almost linear time. Now, if we want to lift these ideas for multiple strings, then it turns out that they will work as it is only if m-1 of the input strings, they are pseudorandom. So here, as because for a given substring from the adversarial string, we try to fix in every pseudorandom string its unique match. That is why we need that m-1 of them should be pseudorandom. And if this is true, then we can fix such a match in all the strings, and then in the rest of the part, we can recurse. But in our work, we consider a much more stronger model where instead of m-1, we just consider one string to be pseudorandom. And for this strong model, we are able to provide strictly below to approximation of alignment distance much more efficiently than the trivial running time. To design this algorithm, we first give another algorithm that provides C times 1 minus 3 theta over 32 approximation of alignment distance in time roughly n to the power m over C, where theta is the ratio between the alignment distance and the length of the input string. So here you can see if the alignment distance is large, so if it is, let's say, omega n, then this theta become constant. So if we take this C to be 2, then if this theta is constant, then we can give strictly below to approximation of alignment distance in time n to the power m over 2, provided, again, the alignment distance is large. So this algorithm is designed using dynamic program and some flavor counting argument. So other than alignment distance, we can also show that this large region algorithm, those ideas can also be extended for computing LCS. So we give an algorithm that provides order lambda approximation of LCS of m strings in time n to the power m over 2, where lambda is the ratio between the LCS, length of the LCS, and length of the input string. So here, if the length of the LCS is large, so if it is again omega n, then this lambda become constant, and in that case, we can provide constant approximation. So for large LCS, we can provide constant approximation of LCS in time n to the power m over 2. So now if we take this m to be 3, so if we consider 3 input strings, then you can see that we can provide order lambda approximation in time n squared. And we can contrast this result with the result of Rubinstein et al., where they provide order lambda cube approximation of LCS for 2 input strings in time n to the power 1.95. So for two input strings, the trivial running time is n square, and for three, it is n cube. So our running time here is significantly lower than n cube, it is quadratic, whereas our approximation guarantee is much stronger. So next, I will briefly discuss our below two approximation algorithm for alignment distance, considering the distance to be large. So in this algorithm, given these m strings, we first divide them into two groups, G1 and G2, where in each group, we are having m over 2 input strings. Now let the alignment distance be d. Now we can design an easy algorithm where what we do, we first try to enumerate or construct each alignment sigma in G1 such that the cost of sigma is bounded by d. Now you can see, as because we have assumed that optimal distance is d in this process, we will also construct the optimal alignment. And once we generate all these alignments, we can send them to group 2 and try to see whether they are also a valid alignment in group 2 and their cost is d in group 2 as well or not. And as because we have generated opt in this process, once we send opt to group 2, in G2 also the cost of opt is d, and so we can output opt. But now the problem with this processing, there can be as many as n to the power m over 2 different alignments of cost d or at most d in G1. And generating one such alignment using dynamic program can take time up to n to the power m over 2. Thus, generating all these alignments can take time n to the power m, and this is not efficient. So this says us that if we use a trivial algorithm where we try to compute all the alignments in G1 that are whose cost is upper bounded by d, then we cannot afford that. So we need to come up with some clever strategy where we don't enumerate all the alignment or construct all the alignments, but rather construct a set of alignments. So here we construct a set of alignments A that follows the specific property. So if we take any pair of alignments, sigma and sigma prime from A, then the set of unaligned characters in string S1 with respect to sigma and sigma prime, their intersection is very small. So their intersection is at most n square over c, where d is n over c. So in a way, what we are saying is in this enumeration process, at every round, given some alignments that we have already generated, we want to find a new alignment which is farthest from the given alignments that have been computed already. So for example, let's start with an alignment. Let's say in the first round, we compute an alignment sigma, and these red characters, they are the set of characters that are not aligned. So here you can see in S1, these are the characters that are not aligned. And given this sigma, in round 2, we want to compute another alignment, let's say sigma prime, such that the cost of sigma prime is bounded by d. And moreover, if we consider the set of unaligned characters in S1 with respect to sigma prime, which is these blue characters, then the overlap between these red characters and the blue characters, that is minimal. And then given the sigma and sigma prime, we can try to generate another alignment whose cost is again bounded by d, and its overlap, the overlap of the unaligned characters in S1 with respect to this new alignment and sigma prime, that is minimal. And now the question is how long this process can continue. We can show using a counting argument that this process cannot continue for more than 2c steps, and that is why we can show that there can be at most 2c different alignments that can be present in this set A. And this way we can bound the total running time, because we can design a dynamic program algorithm that computes this farthest alignment given all previous alignments that have been already computed using a dynamic program in time roughly n to the power m over 2. And as because we do it or we repeat this step at most for 2c times, so the total running time become 2c times n to the power m over 2. And if we consider our distance to be large, so if we consider d to be omega n, then this c is a constant. So the total running time become n to the power m over 2. So now what is left is to argue about the approximation guarantee. So once we have generated all these strings, what we do, we take every alignment that is a part of this set A and send it to group G2. And then we try to find an optimal alignment between sigma and G2, and then output the best sigma. Now to argue about the approximation guarantee, If we consider the case where opt is present in A, then we are in a very good situation. Because if opt is in A, when we send opt to G2, it again matches all the strings in G2, and in that way we can if we output opt, we give cost D. But otherwise, if opt is not present in A, then what we can ensure is that A is containing another alignment sigma, such that the set of unaligned character in S1 with respect to sigma and opt, they have a huge intersection. So they have an intersection of size at least n over 2c squared. And now, though we are not having opt in our set of alignments A, we have sigma, and if we consider sigma as our approximate alignment, then the total objective is upper bounded by 2d minus d over 2c. And as because we have assumed that our distance is large, so c is a constant, you can see that we can provide a strictly below 2 approximation of the alignment distance. So we can also show that all these ideas, they can also be extended for longest common subsequence, and for M strings, we can provide order lambda approximation of their LCS in time n to the power m over 2. So in last few slides, I will give a brief overview of the algorithm that gives us below 2 approximation of alignment distance considering one string to be pseudorandom. Now, before going to that, let's again try to take a recap of the case where m minus 1 strings are pseudorandom and only one string is adversarial. Now, what can happen is that as because all these strings are pseudorandom, if I take one substring from the adversarial string, then in each of this m minus 1 pseudorandom string, this substring has a unique low-cost match. And now once we fix this low-cost match, so it is marked by this red color. So once we fix this match, in the rest of the string, we can recurse. And this way we can ensure that we give an algorithm which runs faster than the trivial one. But this observation completely breaks down once we have just a single pseudorandom string. Because if we take a substring from the pseudorandom string, then in the adversarial string, there can be many substrings with which it can have small distance. So here you can see from the pseudorandom string to this adversarial string at the top, it has 3 different matches. So we cannot use the previous idea. But here we make an important observation. Though from the pseudorandom substrings, in the adversarial string, there can be many different matches. If I take a substring from the adversarial string, then this match is unique. So for each of these 3 substrings in the adversarial string, they are uniquely matched with this red color substring from the pseudorandom string. However, if we consider the optimal alignment, then at most one of these pairs can survive. Okay, so we cannot match all 3 of them together in the optimal alignment. At most one can be matched. And that is why for a pseudorandom substring, if there are a lot of substrings in the adversarial string such that they can be matched with small cost, then as because we can match at most one of them, so for the rest of the pair, we need to take large cost match. So in that case, what we can do, even for the small cost match, if we take a trivial cost estimation, still we stay within our guaranteed approximation. And that is why if there are many matches for the pseudorandom string, if there are many matches in the adversarial string, then we just take a trivial cost estimation even for the low cost match. And otherwise, if there are fewer matches, so it can be more than one, but if there are fewer matches in the adversarial string, then we enumerate all possible m tuples. So you can see this blue color, this shows or this represents one such m tuple. And for each such m tuple, so this is another m tuple. So for each such m tuple, we compute their cost using a dynamic program algorithm. And as because there are few of them, we can do it efficiently and we stay within our time limit. Now, the next step here is that, so for all small cost match, we can compute their cost. And then the next part is, what about the large cost match substrings? Now, for the large cost match substrings, if we just take a trivial cost estimation, then it can give us at most a constant approximation guarantee. But if we want to make sure that our approximation guarantee is strictly below 2, even for this large cost match substrings, we need to provide better than 2 approximation. Now, other than this, there is another challenge. As a priori, we do not have any information about the optimal alignment. We do not know the location of these unique matches. And that is why we also do not know the location and the length of this large cost match substring. So here you can see if this is a unique match, then this first part, this white part is a large cost match substring. Whereas if this is the unique match, then the length and the location of large cost match substring, it changes. So what we do to tackle this situation, instead of taking a single length or single location of this large cost match substring, we take variable sizes, and this way we try to guess the right length and location of the large cost match substrings. And once we have all these m tuples of large cost match substrings, we find their cost using a dynamic program algorithm. But instead of using a trivial dynamic program algorithm, as the cost is already large, we know that we can use our large distance algorithm, and that cannot provide us the exact distance, but it can provide us two approximation of the alignment distance and much more efficiently. Now, once we have all these m tuples of large cost match and small cost match, we can then combine them using a dynamic program algorithm. On top of this, we run another dynamic program algorithm, and overall we can show that with this guarantee that one of the input string is pseudo-random, we can provide strictly below 2 approximation of alignment distance in time roughly n to the power m over 2. So I will finish this talk with a few open questions. So in this work, we are able to break the 2 approximation guarantee if one of the input string is pseudo-random either, or the alignment distance is large. But for the most general case where all the strings are adversarial and the distance is small, the trivial approximation guarantee is still the best. So the 2 approximation guarantee, or the 2 approximation is still the best, what we know. So one nice question is, can we break this 2 barrier for the most general case? Another nice question is, can we really provide very small approximation factor? So can we give an algorithm that gives us 1 plus epsilon approximation of alignment distance in time significantly better than n to the power m? So in time sum n to the power m minus c for constant c greater than 0. Now, for longest common subsequence, we give an algorithm that provides all the lambda approximation of LCS in time n to the power m over 2. So this gives us constant approximation only when the LCS length is large. So another nice question is, can we give constant approximation of LCS in much more efficiently, so when running time n to the power m over c for constant c. So that's all from my side. Thank you.